Hi everyone, this example is question 5 from our exercise. Now the question says that we have an acceleration of a particle given by this function 5t plus 3. So acceleration is not constant. Acceleration will change depending on the elapsed time t. This means we cannot simply use the equations of motion that we developed earlier. We will have to go back to the basic idea of integration and calculus, because we don't know what the formula for velocity will look like when our acceleration is of this function rather than being a constant. So we can't simply write v equals u plus at this time. The question asks us, if the elapsed time is 8 seconds, what is the velocity of the particle and what is the displacement of the particle? So as I just suggested, we will have to write that v equals the integral of a dt. 5t plus 3 is the function. So our integral will be 5t squared over 2 plus 3t plus a constant of integration. Now we evaluate the constant of integration by considering v naught. We were told the initial condition here, v naught equals 6. Considering that v naught equals 6, substituting into my formula here with time 0, the first term will be nothing, the second term will be nothing, and then we have c. Our constant equals 6. So our formula then for v is 5t squared over 2 plus 3t plus 6. We could use that to find the velocity at any particular time. The question said we needed to predict the velocity when t equaled 8. So we're literally substituting 8 into our function. 5 by 8 squared over 2 plus 3 by 8 plus 6. A quick check of the calculator gave me the result 190 metres per second. That's pretty fast, in 0 to 190 metres per second in 8 seconds. This is not any sort of a regular car that I've ever heard of. In fact, we don't even know what it was. It just was some mysterious particle that had an acceleration governed by this formula. Now, let's move on to displacement. So, displacement equals the integral of v dt. Our formula for v, oh, what have I done? Make that go away for a minute. 5t squared over 2. I might write this as 5 over 2 t squared to separate out the constant from the pronumeral. 3t plus 6. Don't forget the dt. So the 5 over 2, the constant will sit there. I'll have t cubed over 3. Now I have 3t squared over 2 plus 6t plus a constant of integration. Now they didn't tell me anything about the initial conditions for x, did they? So I will assume that x naught equals 0. Is that reasonable? Yes, it is, because all it really means is that the origin of my reference system here just happens to coincide with the starting point of our particle, and that's really that's quite a reasonable assumption. If we did assume that x naught didn't equal 0, well, that's just going to overcomplicate things. It could be done, but why make it hard for ourselves? Unless otherwise stated, it is perfectly reasonable to assume that the measuring point starts from where the object starts. It's not only reasonable, it's quite logical to do so. So by considering this, by considering that x naught equals 0, substituting time of 0 here, here and here, these first three terms will disappear. We'll have nothing plus nothing plus nothing plus c. Therefore c equals 0. It's much easier this way. This gives me the conclusion that my formula for x, let's neaten this up a bit, 5t cubed over 6 plus 3t squared over 2 plus 6t. Once again, this could predict the value of x at any time. We were asked in the question to consider a time of 8. 5 by 8 cubed over 6, 3 by 8 squared over 2, plus 6 by 8. And when I did that earlier, I had the answer 570.7 metres. I rounded off slightly. So that's a nice example of how we will do one of these sorts of questions where it is not a constant acceleration. How do I know acceleration wasn't constant? Because they gave me a formula that had time as a pronumeral. Acceleration is literally a function of time. The important thing, and this is our fundamentals, v equals the integral of a dt, and then down here x equals the integral of v dt. That's the two fundamental mathematical statements to remember. And in this particular case, it turned out that v was this function. It won't always look like this, it'll depend on what you start with. And it turned out that x was this function. Again, it'll depend on what you start with as the acceleration. So there will be plenty of questions like this where we start with a different function up here for acceleration. The things in green will be the same, but the things in yellow will change each time as we go through. That's enough for now. Try a few more of these for yourself from the exercise, and don't forget to give me a message on Teams if you get stuck.